This video is designed to give you an idea how to sketch exponential functions and talk about how the variations of the different variables in the sort of general form of the exponential function cause you to transform that graph or to change that graph. So first of all, an exponential function, let's look at a basic one. Something like y equals 2 to the x is an exponential function. And every exponential function has a general look of either growth or decay in a curved fashion. So an exponential function, y equals 2 to the x, we can pick out a couple of important points. We can put in x equals 0. When x equals 0, what we're going to get for y, and of course we can call it f of x as well, so maybe you think of it as f of x is y equals 2 to the x. So if x equals 0, then 2 to the 0th is just 1, so we get the point y equals 1, so we have 0, 1. Now that's going to be the y-intercept, which is where it crosses the y-axis. Now, you can plot some other points. You can give yourself an example. You can say if x is 1, then y is 2. If x is 2, then y is 4. If x is 3, then y is 8, and so on. And you can see that it's growing. But you can also put in fractional x's, so it's a continuous curve, and you can put in negative x's. So if we put in, let's say, -1, then what we have is 2 to the -1, which of course is 1/2. And if you put in -2, you're going to get 2 to the -2, which is 1/4, and so on. So, you know, something very large negative is going to give you a very, very small fraction. So what this graph then is going to look like, it's going to go through the point 0, 1, and it's going to come through here, and it's going to curve upwards in this fashion and get steeper and steeper as you keep doubling each time x grows. And what it's going to do in the negative side is gradually come down towards 0, getting a smaller and smaller fraction. Now it'll never actually reach 0, but it's going to head in that direction. So it's closing in on the x-axis there from above, and eventually you're going to get a fraction that's 1 over 2 to the 1,000th, and then 1 over 2 to the millionth, and so forth. So you get very, very close to 0, infinitely close to 0, depending on how, you know, you just keep getting a bigger x. So that's called the asymptote. And what that means, and I'm going to use, it's usually represented by a dotted line that the thing approaches, and that was done badly, but you get the idea. And the asymptote in this case is y equals 0, and that's called the horizontal, so let me write this out, horizontal asymptote. Asymptote. And what that means is a line that the graph approaches but never touches or crosses. And so in this case, every exponential function is going to have a horizontal asymptote, and it's a question of how that how the graph approaches it. So there's a fairly basic graph. Let's take a look at the next slide. So the original kind of parent graph is actually y equals e to the x. Now e is just a constant like pi. It's an irrational number like pi. It shows up a lot in exponential functions. You know, it's the kind of understood constant that goes in here, and it's actually a number that is approximately 2.71828, etc. It's just like pi. It's an irrational number that goes on forever, and it's not a repeating decimal or whatever. However, just as a benchmark, you know that e is this number that's a little less than 3. And so that means that this graph compared to the last graph would go up more quickly because e is a bigger number than 2. So again, the graph then is going to look something like this, and I'm just going to make a quick sketch, a quick curve, and it's going to look like this. And of course it keeps going, it gets flatter and flatter down here and approaches the asymptote. But in this case, what we're going to get for the intercept, when we put in 0 for x, when we put in 0 for x, we get 1 for y again, because e to the 0th is that. And so what we're going to get is this point 0, 1 again, but it's going to go up more steeply, so that in this case, when x is 1, what you actually get is e instead of 2. So that would mean there's a point here where this is going to be right here. It's going to be 1, e, and so on. And of course, we have again an asymptote down here at y equals 0, in other words, at the x-axis. So let's take a look at what variations we can have on this and see how it's going to change. The general format is going to be y equals a, where a is a variable, e to the x times e to the x. So a is like a coefficient. But we're going to call it e to the x plus b because we could index our x a little bit differently. We could have it give you a higher exponent when you put in 0 for x, and it would be e to the b then. And excuse me. And we'll also put in a c. And let's take a look at what these things do to the graph in subsequent slides. So let's take a look at this graph, y equals 2 to the x plus 3. What is this going to do? Well, we can put in input-output table in, we can put in x and y, and when we put in 0 for x, we get 2 to the 0th, which is 1, plus 3 this time, so we get 4. We also get, if we plug in x equals 1, we're going to get 2 to the 1st, which is 2, plus 3 is 5. Put in 2, we're going to get 4 plus 3 is 7. Put in 3, we're going to get 8 plus 3 is 11, and so on. But notice also if we put in, let's say, negative 1, we're going to get 2 to the negative 1, which is 1/2. So now instead of getting essentially 1/2 and then 1/4 and then 1/8 and closer to 0, what we're getting is 1/2 plus 3 and 1/4 plus 3 and so forth. So we're getting closer and closer to 3. So it turns out that what this allows us to do is draw a nice graph where the asymptote this time is at y equals 3. In other words, the y value never gets below 3. So y equals 3 is the horizontal asymptote again. Sorry for the writing. And what that means is our graph is now coming down, and it's going to be 1 up above the horizontal asymptote. So this is at 1, 2, 3, and so up at 4 is going to be where this graph passes through. And what that means is our graph is going to look like this time, and it's going to come down through 4 and then gradually approach the asymptote of y equals 3. So what that means is we now have a graph that looks very similar, but its intercept, its y-intercept is 0, 4 because it's been shifted up 3 by c. Now obviously if this was y equals 2 to the x minus 3, this whole graph would be dropped 3 below the axis, and your horizontal asymptote would be y equals negative 3. Let's take a look at a couple more variations on subsequent slides. So here's another exponential function, and this one has a equaling 3, so this is a right here, and we have a smaller base. Instead of e, we have 1.3 being raised to the xth power. So what A does is it raises up the graph because it triples every number. But what 1.3 does is it means we're multiplying by 1.3 each time to increase our value. So we're not increasing as fast as we did with E. So this is going to be a little bit of a flatter curve, and yet the A sort of counteracts that, at least at the intercept level. But what you get is a graph that has the same horizontal asymptote. In other words, we still have an asymptote right here, okay, at y equals 0, because as x gets very, very small, very, very large negative, or very far left on the number line, then you're dividing by 1.3 to the millionth power, for example, and it's a very, very small fraction. So once again, you still come down to this, you know, in the deeply negative x's, you're still getting a very small fraction that's approaching 0. However, what you really want to do is consider what the various points are. So let's plug in a few points. If we put in x equals 0, we're always looking for that y-intercept. So you basically want to benchmark your curves and talk about what's going on with finding the y-intercept and knowing where the horizontal asymptote is, and then kind of comparing how steep or how quickly the graph rises compared to y equals e to the x. So in this case, when x is 0, 1.3 to the 0th is, of course, 1, and so we have 3 times 1, or 3, for the value of y. So what we've done versus the graph that would be y equals 1.3 to the x, our intercept is at 3 instead of at 1. And then, of course, if we plug in other values of x, let's put in 1, you're going to get 1.3 to the first power, which is 1.3, times 3, which is 3.9. So you can see it's not going up quite as steeply. And if x is 2, then you're going to get 1.3 squared, which is 1.69, times 3, which is 3 times 1.69. Let's check that out. 3 times 1.69 is 5.07. So you're going to get 5.07. You should check the math on that yourself. But you can see it's not going up quite as fast because it's only multiplying by 1.3 each time you increase x. However, it started at a slightly higher number, and that's because 3 is raising the bar on things, which means it doesn't approach 0 quite as fast, because you're always, whatever fraction you would have had before that was close to 0 is now 3 times bigger. So what your graph looks like is something like this. And I'm going to draw it a little flatter, but it's hard to represent these things. But the idea is that it's going to do this, and it's going to approach 0. And this is the point 0, 3. And you would argue that if you were talking about this, you would say it's a little flatter, meaning not as steep, than y equals e to the x, but it's otherwise a very similar graph. It has the intercept that's shifted up because of the a being 3, and so on. So let's take a look at a couple more examples, and you'll see a little bit about how to settle in and decide what the graph is going to look like. So here's another exponential function. The base now is 0.8, which means that each time you're taking the previous value of that exponential section and multiplying by another 0.8, which means it's decaying this time. So this graph is decaying because your base is less than 1, or the absolute value of the base is less than 1, actually. We'll only be dealing with positive bases here. But the absolute value of 0.8 is, of course, 0.8, and so it's less than 1. Now, what we're going to do is we're going to take a look at what's going on with the horizontal asymptote, and also, once again, with when we put in some values for x. So let's kind of take a quick look at this. 0.8 when raised to some very, very large power is very, very small, which means this time as x gets very big, we're actually approaching 0 for that section of the equation, which means we're approaching 0 plus 3, which means we're approaching 3. So once again, we have an asymptote of y equals 3. Not a very well done asymptote, but there you go. So this is y equals 3 is the horizontal asymptote. But this time, since the problem is decaying, we're actually approaching y equals 3 on the big side here. So of course, let's mark that this is y equals 3. And what we want to do is find out what our values are when x equals various values. So when x equals 0 now, in other words, let's look at the y-intercept, hey, look what happens with the exponent now. It's 0 minus 1, which means it's 0.8 to the negative first power. So 0.8 to the negative first power means 1 over 0.8. So this is actually a number that's slightly bigger than 1. So it's actually 1.25. And so this is going to be 4.25. You can check those numbers out for yourself. But now we actually have the intercept of 0, 4.25. So let's come back and take a look at what that means on the graph. And let's kind of try to sketch this. And of course, we're fairly flat because it's decaying at 0.8 instead of, 0.2 or something like that. So let me kind of resketch this part just a little bit and give us a slightly cleaner version of what we want. So it's going to be something like this, and it's going to continue up that way. And our intercept is at, there's 4. So we're going to say our intercept is at 0, 4.25, 4 1/4. And that's because when x is 0, 0.8 is being raised to the negative 1 power. So it's 1 over 0.8. So when x is 1, just for example then, let's see what happens. Then we have 0.8 to the 0th power, which is 1. And 1 plus 3 is 4. And so what we've got is a point over here that when we're at 1, if we go up here, this point actually is going to be 1, 4, excuse me, 1, 4, and so on. So you should be able to sketch it. And the main thing to recognize is that this is decaying and that it's going to be flatter than parent graph, y equals e to the x, because it's decaying with 0.8 instead of 1 over e. In other words, 1 over e would be the reverse, the decaying version of it, e to the negative x, you could also write it. And so this one is just not decaying as fast, so it's a little flatter graph. So you'd say flatter, but again, it's hard to depict this just sketching it without changing the scale and doing all of that sort of stuff. Let's take a look at one more. So here's one more exponential function, and what we're seeing is that a is -6. Now the negative sign means that every number we get for y is going to be a negative number added to 2 instead of a positive number added to 2. What that means is as this number gets very, very large, as x gets very, very large, we're going to get a very large negative number, which means it's going to be below our horizontal asymptote, which is 2. We'll see that this allows us to kind of come up with another look at this graph in this regard. Now, obviously, when x is causing this -6 times 1.3 to the x power to be very, very small, the number is going to be close to 2. But it's going to be coming up from below it because all these values are going to be, all the values of this part that I've just circled, that's going to always be negative. Okay, so y is going to be some number, some negative number with 2 added to it. So let's take a look at a couple of these values and see what we get. So if we put in, for x, if we put in 0, then 1.3 to the 0th is 1. Then we get negative 6 plus 2, so we get negative 4. So of course the negative 6 causes us to shift our y-intercept substantially again, just as it did in an earlier slide. But we have our horizontal asymptote at 2, and so this is at 1, at 2, so this is the line y equals 2 is our horizontal asymptote. And as x gets bigger, we get more and more negative, and so we have 0, negative 4. Let's plot that one. And what that means is we want to go through this point right here of 0, negative 4. Okay, so we have that as our y-intercept. And of course, it's 1.3 is our exponent, so it's not super steep. 1.3 is less than e, so it doesn't curve quite as dramatically. But within this range, the 6 has shifted it up, and so let's plot. Let's come up with the value for one more point. Let's put in I don't know, 1 for x. Then it's 1.3 times 6, and 6 times 1.3 is 7.8. So it's negative 7.8 plus 2, which is negative 5.8. And so it's gone up, let's see, let's double check all of that. 1.3 times 6 is, of course, 7.8, so it's negative 7.8 plus 2, so negative 5.8. Yes, that's correct. So we're going to have this point, let's call it 1, negative 5.8, so we have that point, which is right there. That's going to be 1, negative 5.8. Okay? But obviously, these values are going to start to head towards 2. As x gets very large negative, we actually have a very tiny negative number that's being added to 2, and therefore it looks like this. So this is going to be flatter than the parent graph. I'm going to write flatter than PG for parent graph, PG for parent graph, with a y-intercept that's 0, negative 4, and a horizontal asymptote of y equals 2. And that would be a kind of a sufficient sketch. And recognizing that this is upside down, meaning that it comes, it is below the asymptote, and that's because of the negatives of a being negative at negative 6. So it's upside down since a is less than 0. Okay? I hope this has been helpful.